The power company likely used a specific formula to determine the monthly kvar correction required to achieve a 90% power factor. This formula is kvar correction equals the quantity of actual kVA multiplied by the quantity of 0.9 minus the actual power factor, multiplied by 1000, divided by the voltage. Let's break down the components of this formula. Firstly, actual kVA represents the actual kilovolt amps used during the billing cycle. Secondly, the actual power factor refers to the power factor observed during that billing cycle. Thirdly, 0.9 represents the desired power factor, which in this case is 90%. The value 1000 acts as a conversion factor, changing from kilovolt ampere reactive to volt ampere reactive. Finally, voltage is the voltage of the electrical system being considered. Let's illustrate this with an example. Imagine the actual kVA used during a billing cycle was 1000, the actual power factor was 87% or 0.87, and the voltage was 480 volts. Plugging these values into the formula, we have kvar correction equals the quantity of 1000 multiplied by the quantity of 0.9 minus 0.87. multiplied by 1000 divided by 480. This simplifies to kvar correction equals 52.8 kvar. Now let's discuss how to perform a cost comparison between the scenario before capacitor installation and the scenario after capacitor installation. A suitable formula for this is cost savings equals the quantity of kvar correction multiplied by peak demand, multiplied by IOs of operation, multiplied by cost per kilowatt hour, divided by 1000. Again, let's define each component. Firstly, kvar correction is the kvar correction calculated using the formula we discussed earlier. Secondly, peak demand represents the highest demand observed during the billing cycle, usually measured in kilowatts. Thirdly, hours of operation refer to the number of hours the equipment operates during the billing cycle. Finally, cost per kilowatt hour is the price charged by the power company for each kilowatt hour of energy consumed. Consider this example. If the kvar correction was 52.8 kvar, the peak demand was 1000 kilowatts, the hours of operation were 720, and the cost per kilowatt hour was 10 cents, the cost savings would be calculated as follows. Cost savings equals the quantity of 52.8 multiplied by 1000 multiplied by 720 multiplied by 0.10 divided by 1000. This results in a cost savings of $37.46. This calculation demonstrates the potential savings that can be achieved by installing capacitors to correct the power factor to 90%. In this instance, it could save you $37.46 per billing cycle. To elaborate further, understanding and applying these formulas allows for a quantitative assessment of the benefits of power factor correction. Power factor correction, often achieved through the installation of capacitors, improves the efficiency of electrical systems. A low power factor indicates a significant phase difference between voltage and current, leading to increased current flow for the same amount of useful power. This increased current results in higher losses in the distribution system, and can also lead to voltage drops. Power companies often penalize consumers with low power factors because they must supply more current to deliver the required power. Correcting the power factor brings the voltage and current closer in phase, reducing the current required for the same power output. This reduction in current minimizes losses, improves voltage regulation, and reduces the load on the power company's infrastructure. The kvar correction formula helps determine the appropriate size of capacitors needed to achieve a target power factor, typically 90% or higher. The cost savings formula allows for a financial justification of power factor correction projects by quantifying the reduction in energy costs. To accurately apply these formulas, precise data is crucial. Actual kVA, actual power factor, peak demand, hours of operation, and cost per kilowatt hour should be obtained from utility bills, power monitoring systems, or equipment specifications. The voltage used in the kvar correction formula should be the actual operating voltage of the electrical system, which can be measured using a voltmeter. When evaluating the cost savings, it is important to consider the lifespan of the capacitors and any maintenance costs associated with their operation. Capacitors have a finite lifespan and may need to be replaced periodically. Maintenance costs can include inspection, cleaning, and testing. The return on investment for a power factor correction project depends on several factors, including the initial cost of the capacitors, the installation costs, the energy savings, and the lifespan of the capacitors. In some cases, the payback period can be relatively short, making power factor correction a financially attractive investment. In addition to cost savings, power factor correction can also improve the reliability and performance of electrical equipment. By reducing the current flow in the system, power factor correction can reduce the stress on cables, transformers, and switchgear, extending their lifespan and improving their reliability. It can also improve voltage regulation, which can prevent equipment malfunctions and improve the performance of sensitive electronic devices. There are several types of capacitors that can be used for power factor correction, including fixed capacitors, switched capacitors, and automatic power factor correction systems. Fixed capacitors are installed at the load and provide a constant amount of reactive power compensation. Switched capacitors are switched in and out of the circuit as needed to maintain the desired power factor. Automatic power factor correction systems use a controller to monitor the power factor and automatically adjust the amount of reactive power compensation. The choice of capacitor type depends on the specific application and the variability of the load. Fixed capacitors are suitable for loads that are relatively constant, while switched capacitors and automatic power factor correction systems are better suited for loads that vary significantly. When selecting capacitors for power factor correction, it is important to consider the voltage, current, and frequency of the electrical system. The capacitors must be rated for the operating voltage and current of the system and must be compatible with the system frequency. It is also important to consider the harmonic content of the electrical system. Harmonics can cause capacitors to overheat and fail. If the system has significant harmonic content, it may be necessary to install harmonic filters to protect the capacitors. Power factor correction is an important aspect of electrical system design and operation. By understanding the principles of power factor correction and applying the appropriate formulas, it is possible to improve the efficiency, reliability, and performance of electrical systems and reduce energy costs. Remember to always consult with a qualified electrical engineer when designing or implementing power factor correction systems. Understanding reactive power is essential for grasping power factor correction. Reactive power, measured in volt-ampere reactive, is the power that oscillates between the source and the load without doing any real work. Inductive loads, such as motors and transformers, consume reactive power, which causes the current to lag behind the voltage. Capacitive loads, on the other hand, generate reactive power, which causes the current to lead the voltage. A purely resistive load has a power factor of 1, meaning that the voltage and current are in phase and all the power is doing useful work. Inductive loads have a lagging power factor, while capacitive loads have a leading power factor. The power factor is the cosine of the angle between the voltage and current. A power factor of 0.9 indicates that the current lags the voltage by an angle whose cosine is 0.9. The lower the power factor, the greater the phase difference between voltage and current and the more reactive power is present in the system. Power factor correction involves adding capacitance to an inductive circuit to offset the inductive reactance and bring the power factor closer to 1. This reduces the amount of reactive power flowing in the system and improves the efficiency of the circuit. The amount of capacitance needed to correct the power factor depends on the amount of inductive reactance in the circuit and the desired power factor. The kvar correction formula provides a way to calculate the required capacitance based on the actual kVA, actual power factor, desired power factor, and voltage of the system. Installing capacitors to correct the power factor can provide several benefits, including reduced energy costs, improved voltage regulation, increased system capacity, and reduced equipment losses. Reduced energy costs result from the lower current flow in the system, which reduces the losses in cables, transformers, and switchgear. Improved voltage regulation prevents voltage drops and improves the performance of sensitive electronic devices. Increased system capacity allows more load to be served by the existing electrical infrastructure. Reduced equipment losses extend the lifespan of electrical equipment and improve its reliability. The cost savings formula provides a way to quantify the economic benefits of power factor correction by calculating the reduction in energy costs. A formula takes into account the kvar correction, peak demand, hours of operation, and cost per kilowatt-hour. The kvar correction represents the amount of reactive power compensation provided by the capacitors. The peak demand represents the maximum power demand during the billing cycle. The hours of operation represent the number of hours the equipment operates during the billing cycle. The cost per kilowatt-hour represents the price charged by the power company for each kilowatt-hour of energy consumed. By plugging these values into the formula, it is possible to calculate the cost savings resulting from power factor correction. In addition to the economic benefits, power factor correction can also improve the environmental performance of electrical systems. By reducing energy consumption, power factor correction can reduce greenhouse gas emissions and conserve natural resources. It is important to note that power factor correction is not always necessary or cost-effective. In some cases, the cost of installing and maintaining capacitors may outweigh the benefits of power factor correction. A thorough analysis of the electrical system should be performed to determine whether power factor correction is justified. This analysis should take into account the load characteristics, the power factor, the energy costs, and the cost of capacitors. If power factor correction is deemed to be beneficial, the appropriate type and size of capacitors should be selected based on the specific requirements of the electrical system. The capacitor should be installed in accordance with applicable codes and standards. Regular maintenance should be performed to ensure that the capacitors are operating properly and providing the desired power factor correction. Power factor correction is a valuable tool for improving the efficiency, reliability, and performance of electrical systems. By understanding the principles of power factor correction and applying the appropriate techniques, it is possible to reduce energy costs, improve voltage regulation, increase system capacity, reduce equipment losses, and improve the environmental performance of electrical systems. Furthermore, consideration should be given to the placement of capacitors within the electrical system. While individual correction at each inductive load is often ideal, it may not always be practical or cost-effective. Group correction, where capacitors are installed at the distribution panel serving multiple loads, can be a suitable alternative. Central correction, where capacitors are installed at the main service entrance, provides power factor correction for the entire facility. The choice of placement depends on the load characteristics, the distribution system configuration, and the desired level of power factor correction. Another factor to consider is the potential for overcorrection. The overcorrection occurs when the capacitance is too large, causing the power factor to lead instead of lag. Overcorrection can lead to voltage instability and other problems. It is important to carefully select the size of the capacitors to avoid overcorrection. Automatic power factor correction systems can help prevent overcorrection by automatically adjusting the amount of capacitance as needed to maintain a desired power factor. Harmonics, as previously mentioned, can significantly impact power factor correction. Nonlinear loads, such as electronic devices and variable frequency drives, generate harmonics, which are currents and voltages at frequencies that are multiples of the fundamental frequency. Harmonics can distort the voltage and current waveforms, leading to a lower power factor and increased losses. Capacitors are susceptible to harmonics, which can cause them to overheat and fail. If the electrical system has significant harmonic content, it is necessary to install harmonic filters to protect the capacitors and improve the power factor. Harmonic filters are designed to block or reduce the flow of harmonic currents, preventing them from entering the capacitors. There are several types of harmonic filters, including passive filters, active filters, and hybrid filters. Choice of filter type depends on the harmonic content of the electrical system and the desired level of harmonic mitigation. Power factor correction is an ongoing process. The load characteristics of an electrical system can change over time, which can affect the power factor. It is important to periodically monitor the power factor and adjust the capacitance as needed to maintain a desired power factor. Power monitoring systems can be used to continuously monitor the power factor and provide alerts when the power factor falls below a certain threshold. These systems can also be used to track energy consumption and identify opportunities for further energy savings. In conclusion, power factor correction is a complex but essential aspect of electrical system management. By understanding the principles of power factor correction, applying the appropriate formulas, considering the various factors that can affect power factor, and implementing effective power factor correction strategies, it is possible to significantly improve the efficiency, reliability, and performance of electrical systems, reduce energy costs, and promote environmental sustainability. Remember, consulting with qualified professionals is crucial for proper design and implementation of power factor correction solutions.